In part 2, we're going to draw a function that's continuous over all real numbers and has the following properties. So the first property is that the first derivative is greater than 0 for x less than 4. And so since the first derivative is greater than 0, I know that this means that the function needs to be increasing on that interval. Then I also need that f of negative 4, the derivative at negative 4 is undefined. Not f, sorry, but the f prime, the derivative. This function needs to be continuous, so I can't have any holes. I can't have any asymptotes, because then it would be a discontinuous function. So if I want the derivative to be undefined, but still continuous, this means that it needs to be sharp. So an abrupt change, there can be many ways of making sharp. It can just be a V shape, or it can be more of that curl into that point shape. One of those two sharp has to happen. Of course, they could be in the other orientation. We'll figure out which of those is going to be appropriate as we look at more details. Right now I know sharp, I know increasing. Let's look at the rest. I know that the derivative is going to be less than 0, so negative, so that means decreasing. Then I know the derivative is going to be greater than 0, so positive derivative means increasing. And the derivative is equal to 0 at these two places, so that's going to be, instead of the sharp undefined, that's going to be smooth. If it's an extrema, it's going to be smooth. So something that's going to be one of those two smooth shapes as it curves gently towards an extrema. And then again, I don't know that they're going to be extrema, right? They could possibly be that third case where they were critical values, but they were not actually extrema, but something that's going to be smooth. I don't know the shape yet, I just know smooth. Look at the shape from the increasing and decreasing pieces. Then we have that the derivative is greater than 0, so again, that's our increasing. Okay, so I'm going to put my function together, starting with values that are less than negative 4. So I'm going to push this up for a second. Starting with values that are less than negative 4. The function needs to be increasing. So I'm going to draw something that's increasing up until it reaches a value of 2. So I'm going to be drawing between negative 4 and 2 right now. Okay, and I need to be increasing and then decreasing. I'm just tracing with my finger for a second. I'm going to be increasing and then decreasing. There's many ways to increase and then decrease, but I need to increase and then decrease in a way that at negative 4, sorry, I'm actually looking at negative 4. Let me rephrase this. I need to be increasing before negative 4. I'm looking just at negative 4, increasing before negative 4, and then at that negative 4 is where I turn around and begin decreasing. So I'm going to be decreasing over here. So good thing I was using my finger to draw. So I'm increasing and then decreasing. Now at negative 4, instead of being smooth, we're going to be sharp. So for this first piece, we're going to have something that is increasing until I reach, I don't know what the y value is, that's not necessary, but until I reach an x value of negative 4, and then I begin decreasing. I have a sharp turnaround because of the undefined first derivative. Okay, now I need to read a little further. I'm going to continue decreasing now until an x value of 2. So I'm going back to my x value of 2, continue decreasing. When I get to that x value of 2, I will be smooth. Also, when I get to the x value of 2, we're going to turn around and be increasing. Okay, so I think I can do that. So we're going to be decreasing until 2, and then increasing. And again, it doesn't matter what the y value was. The only reason I stuck it above the y-axis there is just so I didn't like run into the number I put. Doesn't matter where it was. I could have pulled it all the way down and had some kind of turnaround. The y values right now are not relevant. It's the location is all I know, and then whether it's an extrema. Okay, so we're going to be increasing now. We have hit 2. We're going to increase between 2 and 5. So here's 5. Okay, now at 5, again, we need to be smooth, and at 5, we're going to continue to increase. But I do have to have a place where the derivative is 0. So I'm going to flatten out in a cubic type swish, and then continue to increase. So the derivative is actually 0 right there, but I continue to increase on both sides. So the 3 points of interest that I really need to pay attention to, again, are, I have a point of interest where I had a critical value. So I have a point of interest at these 3 places. And at these 3 places, I need to have the sharp, smooth behavior. And then beyond those 3 places, I also need to maintain my increasing and decreasing. So I had to be increasing for x values less than -4. I needed to be increasing for x values between 2 and 5, and I needed to be increasing for x values greater than 5. I also needed to be decreasing for those x values between -4 and 2. And so we have all of our conditions satisfied. Putting all of that together from 4.1 and 4.2, let's take a look at this graph. Okay, this is a graph that has lots of things labeled. It has absolute mins and absolute maxes. So it has an absolute minimum at A. This is the lowest y value that this graph achieves. And it has an absolute maximum up here at C4. That's the highest that it achieves. Okay. The absolute minimum is at an endpoint. The absolute maximum is at an interior point. Since it's an interior point, that point is also a local maximum or relative maximum. There are a few other local extrema. There's a local maximum at C2, and there's a local minimum at C3. Now, these 3 interior points were critical values, but they are critical values for different reasons. We have the first one that is a critical value where the derivative is equal to 0. Then we have a critical value again where the derivative equals 0, and then we have a critical value where the derivative is undefined. Notice that those 3 are extrema, but they are not the only critical values. We have more critical values that happen over here at C1 that is a critical value because the derivative is 0 there, but it did not turn out to be an extrema, similar to x equals 5 from the previous graph. We have another critical value over here at C5 that was definitely a critical value, but again turned out to not be an extrema because the function was decreasing on both sides. The other things that we know and can now label are the intervals of increasing and decreasing. So this function is increasing, and you would have to separate this. This is increasing from A to C1, and then increasing again from C1 to C2. It is not increasing at C1 because at C1 the derivative is equal to 0. 0 is not a positive value. So this would be 2 separate intervals of increase. Then you have another interval of increase over here between C3 and C4. Finally, we would have a, what color have I not used? Here we go. Finally, I have intervals of decrease between C2 and C3. I have another interval of decrease between C4 and C5. Separate that from the interval of decrease we have between C5 and B. I have 3 intervals of increase and 3 intervals of decrease. So we can tell all of those things about the graph by knowing things about the derivative and its sign, whether it's equal to 0, whether it's undefined, whether it's positive, and whether it's negative. Putting all this together gives us the procedure for the first derivative test. The goal of the first derivative test is to find intervals of increase and decrease and to classify critical values as local extrema. Okay, so the first derivative test starts with finding the domain. I need the domain before I find the derivative because the critical values need to be values where the first derivative is equal to 0 or fails to exist in the domain, right? I only look for values that are in the domain of the original. Those things I have already practiced before in a previous section. So new to this test, I've already done those before. New to this test is step 4, constructing this table. So I'm going to take my critical values and partition this table. So we're going to partition at critical values, partition the domain at critical values, and then we will pick a test value in the interval, determine the sign of the derivative, and then state whether or not it's increasing or decreasing. Once I have my table, I'm going to be able to identify the local extrema based on how these two things change. So if it changes from positive to negative, so increasing to decreasing, I have that maximum classification. If it changes from negative to positive, I have that decreasing to increasing, so I have the local minimum. Okay, so these two things are going to help us classify critical values. I've already practiced finding them. Now I'll be able to classify them using the first derivative test. And finally, at the end of this page, we've got one more theorem. Theorem 4.9 says that if I have a continuous function that has exactly one local extrema, if the local occurs at C, then I have an absolute max. Sorry, if I have a local max and I have absolute max. If I have a local min, I have an absolute min. So if I have exactly one local extrema, that means that my function turns around one time. So if my function turns around one time at an interior point, doesn't matter where my endpoints are, if I have an interior extrema, there's only one interior extrema, then it has to be the absolute as well. I can't have just one turnaround no matter how I cut my function. If there's only one turnaround, that turnaround will be both local and absolute. So that's what that last theorem means.